So, in the last few lectures, we are going to look at an important topic which talks about. So far we have been looking at individual problems and we try to design good algorithms, or we have looked at good algorithmic techniques, right? Greedy, divide and conquer, dynamic program. Now we are going to look at somehow a class of problems and argue about them, okay, and find some relationship between them. And so we have seen problems like, sorting, selection, shortest paths, matrix multiplication, and I am just sort of summarizing whatever we have seen, right? Euler tour, inner, all pair, shortest paths, various kind of problems, and looked at algorithms for them. And typically, one property for these kind of problems we have seen is they have a running time which is like some, n cubed, or more precisely n to the c, where c is a constant. Okay. Typically the constant is at most 3. I don't think, maybe 4, right? Not more than that. The kind of problems we saw. And we also saw a couple of problems where n was in the exponent. Do you remember problems? Yeah, I'll come to that later. When knapsack was one, chromatic number, right? Chromatic number and we saw an algorithm was something like 3 power n, where n was in the exponent. And I also, another problem we saw was set cover, which had a running time of 2 power n, and where n was in the exponent. Okay. So one thing, so clearly we know, I mean, in fact, if you remember my first lecture, I said for some large n, even n square is useless. Okay, we really need, in the world of big data where n is like 10 power 10, n square itself takes huge number of years, whereas n log n is a good algorithm. But for moderate values of n, these are reasonably okay, but 2 power n, 3 power n tend to be pretty bad. I'll show you some table which explains how bad this 2 power n, 3 power n can be. So somehow we want to, so one question is, are they really hard problems, or is it just our inability to come up with faster algorithms, right? That's the question we want to address, and that's the question this theory of NP completeness in some sense addresses it. Okay, so we're going to call P as a set of problems solvable by an algorithm in time polynomial in input size. Okay. There are lots of things that require some explanation, though I mean, so far whatever we understand, when we say problems, it's these kind of problems. When we say solvable by an algorithm, the kind of an algorithm we're talking about, okay, and input size, we understand, we think we understand, okay. You're sorting n inputs, input size is like n, okay. It's not quite true, but we'll come to that, but that's sort of an informal thing. Now this actually has a very formal definition. If you have gone through a course on theory of computing, then I can say languages acceptable by a deterministic Turing machine in time polynomial in input size. Okay. So, people who have not seen what a Turing machine is, I mean, if you understand what a Turing machine is, this is as formal as it can get. Okay. We are working with some very informal definition of problems and algorithm, but they have a formal meaning. So, Turing machine is like the deterministic finite automata we saw in the string matching example. It's again like a machine which has a certain alphabet, states, and at every point, a machine can read and write symbols, move left and right, and eventually it goes and accepts the string like the finite automaton, but it is a lot more powerful because it can move left and right, it can read and write. Okay. I don't want to say anything beyond that, but it's for us this kind of an informal definition is enough, but it's important to know that there is a formal definition. Okay. Input size is something I have to make it clear. So, yeah, what is input size? So, input size you know what your input is, just take a good efficient encoding of the input and look at its size of that. Okay. So, for the most part assume you have a binary encoding of the input. Okay. Size of the binary encoding of so if I am talking about a graph problem, an adjacency matrix gives you an input size of n square. Okay, that's pretty reasonable. If I am talking about the sorting problem, what is the input size? We have been informally using n as the input size, but it is more precisely n times log of the maximum size of the input or something like that. Okay. But if it is polynomial in n, then it is also polynomial in n times log of something. So, that is the reason we did not bother so much about worrying about it, but it is important. It is important in particularly in numeric problems, right. Knapsack is one example, where when we said we had, for example, for knapsack, if you recall our problem, you had n objects, each one had a size, and we had a capacity of W, and we want to pick as many objects as possible and fill up the knapsack. Without loss of a generality, we can assume the sizes are of value at most W, because anything which size is more than W, throw it away. So, then the input size would be n times log W, right. But we had an algorithm whose running time was n times W, right. Even though it looks like a linear time algorithm, it is not even a polynomial time algorithm. Okay. It is an exponential algorithm, because on the input size, it's so a polynomial algorithm would be like n log W polynomial in that. Okay. But W is 2 power log W. So, it is exponential in the input size. So, this is not an polynomial time algorithm, and that is where this input size plays a role. Okay. Another kind of problem where input size plays a role is in numeric problems. Let us say I ask, given an integer n, is it a prime? Okay. What would be your naive algorithm for it? Okay, I will come back to this exponential algorithm. So, naive algorithm would be checking for divisors of n, right, starting from 2 up to how far you want to go. Yeah, you can actually go up to square root of n, because if the number is not a prime, it must have a factor within root n, because it will have at least 2 factors, not both can be above root n. So, try from check for I going from 2 to square root of n whether I divides n. Okay. So, assuming a division is a constant time operation, this is like a root n time algorithm. Okay. Sounds like a sublinear algorithm, but it is not. Why not? No. What is the input size? What is the input size? Log n, right? Because binary encoding of n will take you log n. So, a polynomial algorithm, when I am demanding, I expect it to be polynomial in log n, and then this is reasonable, because let us say I am talking about a 200 digit number and I want an efficient algorithm to be polynomial in 200, not the value of the number, then that may not be an efficient algorithm. Okay. So, size of the number, size of the encoding is important. So, it is a so input size here is log n. So, a polynomial algorithm for this would be polynomial in log n. Okay. This was long open, for centuries people were looking for a polynomial time algorithm until it was settled by a group in IIT Kanpur, Manindra Agarwal, Kayal and Saxena about 15 years ago, I think, maybe 20 years ago now. Yeah. So, that was their famous breakthrough result from India to come up with the poly log n, right, poly in input size algorithm to test whether a number is prime. Okay. Okay. So, let us come back here. We have looked at problems which are in solvable, okay, problem solvable in algorithm time polynomial input size. We have seen a number of problems, but we have also seen problems where the running time is exponential in n. Okay. So, what we would really like, Alt tab, can you do full screen? Yeah. So, for those problems for which we have this very inefficient exponential algorithm, what we really would like to show, no, if you come up with such a problem in real life, you do not want to do this. You do not want to say, this is the best I can do. Ideally, what you would want to say is that to prove a lower bound, right? We have seen lower bounds in very early on, adversary lower bounds, very Mickey Mouse lower bounds, right? We showed n log n, n square, but that's sort of our limits on how much we can show using lower bounds. So, ideally what we would show is that set cover or chromatic number for which I had a 2 power n algorithm. The problem is so hard, it is not just me that there is, I can prove a lower bound that such a problem would require 2 power n time. Well, we can't say that as well. We do not have machinery to prove such lower bounds, like non-polynomial lower bounds. We can prove lower bounds for linear n square, but so far we do not have enough machinery to prove such lower bounds. Okay. But what we will see in the next 2-3 lectures is notion of this notion of NP completeness, which sort of groups these problems together. Not just this problem, we will say that, oh, set cover is related to some 100 other problems for which we do not have efficient algorithm. So, somehow we believe that this problem is inherently hard because there are so many people working. So, at the end of learning about NP completeness, what you can show is this. You can go to your boss and say, I can't find an efficient algorithm, but there is no use for you to fire me and hire somebody else, because neither can all these famous people who have been working on this problem. Okay. So, that is this theory of NP completeness we will get to, if not today, maybe tomorrow, which somehow shows that these problems which we have not been able to get polynomial time algorithm, some of them are inherently hard because they belong to a group, a class of problems called NP complete. Okay, now why do we care about this polynomial time so much, right? So here is an illustration that if your problem size is, let's say, 50 and you have a linear time algorithm. Okay, this is from a table about 40 years ago. Okay, computers were much less powerful, but let's translate to today's computer later. Let me go over this. So if you have a linear time algorithm on a problem of size 50, it will take 0.005 second. N square algorithm will take 0.0025. N power 5 algorithm will take 5 minutes. 2 power n algorithm will take 35 years, and 3 power n algorithm will take 2 into 10 power 8 centuries for a problem of size 50. Okay. This calculation is exactly what we did in more or less the first lecture. You divide just 2 power n, plug in your 50, that's a number of steps, divide by how many steps a computer can make in 1 second, and you will get the number of seconds, convert it. Okay. So this is a story. If a problem of 60, if you have a 3 power n algorithm, the chromatic number for n even 60 is going to take you so many years. Okay. This is 40 years ago. The computers are, let's say, 1,000 times more powerful. Okay, so it's not going to take you 10 power 13 centuries, but it will be like 10 power 10 centuries, okay, or 10 power 9 centuries. Okay, that's absolutely no consolation. Yes, computers have become more powerful, but the problem sizes have also increased now that you should really look at n equal to 100 or 200, and you don't want to think about them. Okay, so more importantly, you can see this big jump between n power 5 and 2 power n, okay, and 3 power n. Okay, so this is one reason computer scientists are obsessed with this class of problems, polynomial time. Okay, there are a lot of other reasons. One is that it's very robust under different models of computation. Okay, so I said deterministic Turing machine, but throughout this course, we did not design Turing machine algorithm for sorting or shortest path, or we were actually working in what is called a RAM model, random access machine. You have the registers, you can go access a number, do this kind of thing. But it turns out any algorithm which you can simulate in RAM model can be translated into a Turing machine with some overhead in time. But if that is polynomial, this is also polynomial. Okay. So in that sense, polynomial class is robust under various different definitions and models, and it's a robust class, and it somehow defines feasible computation. Okay. So that's the reason why we care about polynomial time, but we are left with exponential problems for which the best known algorithms are exponential, and we don't have lower bound machinery, but we have something in between, and that's what we want to get to. Okay. Yeah, so here this is also another illustration that even if your computers get faster and faster, if you have a computer which is 1,000 times faster than what it is today, if you can solve a problem of size n6 by this algorithm, if you have 1,000 times faster, you can solve a problem of size plus 7 in 1 hour. For a linear time algorithm, you can, for an n square algorithm, you can solve a problem of size roughly 30 times whatever you can do now in 1 hour as the computers. So the point is that even just computers getting powerful is not good enough. You want an algorithm to get more efficient. Okay, fine. So, right. So now, so I define this class P. Let's define class NP Okay, so first of all, another thing, we are talking about languages accepted by a machine, which means that, given a string, the machine will say yes or no. Okay. So, that means we are actually going to be focusing on decision problems. They have yes or no answer. Okay, so sorting is not a decision problem. You can't just say sort n numbers. Is the list sorted? Is the decision problem. Okay, for these kind of machine acceptance reason, we are going to focus on decision problem for this theory of NP completeness. Now, that's not too much of a restriction, because I mean ideally I would be interested in find the shortest tour, or the set cover tells you, or find the minimum number of colors, right, is what I am interested in. So, that is sort of the optimization problem. But how do I use decision problem to solve the optimization problem, right? So, suppose, okay, so come back to the graph coloring problem, chromatic number, you want to find the minimum number of colors to color the vertices, okay. But I say no, I do not like that kind of problems, I am going to ask only for a decision problem. So, I will convert it into, is the graph colorable with k colors, okay. How do I use this? If I have an efficient algorithm for this, how can I use this to solve the optimization problem? Just run 1 2 3, and the smallest place where you get S is what you are going to get. So if the decision problems are solvable efficiently, you can solve the optimization problem also efficiently by repeatedly using this decision problem algorithm. So, our hardness theory is also going to talk about decision problems. We are going to say even the decision problem is hard, which in turn will imply that the optimization problem will be hard. Okay. So, we are going to restrict to decision problem, then it is easy to talk about, given this input, is it yes or no, right. So, will the machine accept or not. So, what is NP? For people who understand Turing machine, it is very easy to say languages accepted by a non-deterministic Turing machine in polynomial time. Okay. So, but for our informal algorithms language, how do I write it? But so again, important point is NP, N does not stand for non polynomial time. Okay, it is non-deterministic polynomial time, because we do not know whether it is non-polynomial time until somebody proves that these problems are hard. We do not know that yet. Okay. So, what is non-deterministic polynomial time? So, let me just write it in this: problems for which S answer has a poly length proof, or also called certificate, verifiable in poly time. Okay. So, we are talking about decision problems. So, the problem has a yes or no answer. Okay. So, now when do I call a problem to be in NP? Well, if the S answer has a easily verifiable proof or a certificate, right. So, easily verifiable all means in polynomial time. So, you can give me a proof which I can verify in time polynomial in the input size. Okay. screen ಎತ್ತಿಲ್ಲ ನನ್ನ ಬೋರ್ಡ್ ಯೂಸ್ ಮಾಡಿ. So for example, I ask the question, is the number composite? Okay. So the same algorithm check for I equal to 2 to n whether I is divisible by n will work because it answers prime. So whenever it's not a prime, it's a composite. So it's again, this is not a polynomial time algorithm as we discussed because the input size is log n. But okay, but now I am not interested in a solution. I am just saying for the S answer, can you give me a proof which I can verify easily? So what would be a proof for the fact that the number is composite? So think of it as this is a homework for you. I give you a large 200 digit number. I ask you whether it's composite. You are allowed 1 year. Okay, because I am not counting on the time you have spent to come up with the certificate. But after 1 year, you come back and say, yes, it's composite. Here is why. And me with limited resources should be able to look at your proof, verify it, and convince myself. So what would be a proof? Give a divisor, right? You just say 247 divides your number. Okay, that's a short proof. And what do? I just divide and verify. So that's what it means by S answer has a poly length proof verifiable in poly time. Right? So is the number anything in P is also right? Let's observe that. So, okay, so this question of is the number composite is in NP. Okay, let's put this in. Okay. You can, I mean, you can do something very similar for primes also, but that's not trivial, right? I give you a large prime number and I ask you, is it prime? You know, I give you a long time, you come back, what is an easy proof that it is a prime? Well, it turns out using some number theory, Fermat's last theorem, blah, 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 you can come up with some proof, but it's not that easy. So before prime was proved to be in poly time solvable, it was shown to be in NP, which means that there is an easily verifiable proof first. Okay, that itself was a paper which uses some repeated applications of Fermat's last theorem. It gives a proof which you can verify. But notice that anything in P is in NP, right? Do you see this why? Again, if you understand in the language of Turing machine, it's immediate because a deterministic Turing machine can solve it, then a non-deterministic Turing machine will also solve it. But in this language of proof and verification, how do you show that P, anything in P is an NP? Yeah, exactly, right? So you don't, so here is a problem, and it says S answer you give, and how do I verify? You don't need to give me a certificate. I run the polynomial time algorithm and check. Because it is deterministically poly time, I run the polynomial time algorithm, I can verify convincingly, even without a certificate. So P is contained in NP. Let's look at more examples, right? In fact, it's useful to know. So given a graph G and some two vertices ST and an integer k, I ask, does there exist a path of length at most k between S and T? Okay, undirected. So what is it, NP or?
We don't even need a certificate. We can just run that column, but someone has to give the certificate for us to verify.
No. So let's look at this problem. Okay. in fact, this will illustrate. Suppose I ask this question. Does there exist, so given a graph, undirected graph, and two vertices S and T and an integer k, and I ask, is there a path of length at most k from between S and T? Okay. So is it in P or NP or what? This is in P, right? This is in P because it's an undirected graph. You can run a BFS from S and see whether T reaches, and you'll get the length of the shortest path. And hence it's in NP, I claim, because what do I need? The S answer has a poly-length proof verifiable in poly time, right? So the S answer, yes, there is a path of length at most k. Suppose you say that. In fact, if the problem is in P, even the no answer is verifiable anyway, right? So what do? I run my BFS algorithm. I don't need a certificate, nothing from you. I run because there is a polytime algorithm. My only restriction is I am a polytime machine. So I run my polytime algorithm on your graph and check whether there is a path of length at most k between S and T, and if it is, I say yes. Okay. But if I turn the question and ask this, okay, so let me make sure this is in P, right? But if I ask the question, does there exist well, we didn't discuss this problem. There is no efficient algorithm. In fact, you can't apply dynamic programming. There is no optimum substructure. This is something you can verify, right? If you have a path of length, this is like shortest path we are talking about, and this is longest path. And if you have a vertex here, and this is the longest path between S and T, it's not necessarily true that this is the longest path here and this is the longest path here, right? But I can write a simple example. Longest path between A and C is ABC, but doesn't mean that this is the longest path between A and B because I have a longer path. Okay. So, none of the algorithms that we have seen work. Not just that, we don't have at the moment a polynomial time algorithm. Okay. But is it in NP? Yes. What would be a proof you can give? You give me a sequence of vertices, and my job is to just check that this is every adjacent pair is adjacent and the total length is at least k. So the S answer has a poly length proof, which is the sequence of vertices, which I can verify in polynomial time. So this problem is an NP. Another contrasting example is given G, does G have an Eulerian cycle? A cycle that visits every edge exactly once, right? You've seen efficient algorithm, even linear time algorithm. So this is in P. But if I ask, does it have a Hamiltonian cycle? And what's a Hamiltonian cycle? A cycle that visits every vertex exactly once. See, for Eulerian, there is a very simple, nice characterization that every vertex has an even degree. You can even just check the degree of every vertex. Here, there is no such characterization. We don't know. So, is there a cycle that visits every vertex exactly once? Comes back to where it started with. I don't care about missing edges, but that problem, we don't know an efficient algorithm. But is it in NP? So, what would be a proof? If I give you a graph and I ask is there a Hamiltonian cycle and you come back and say yes, what would be a proof? The cycle itself, right. You give the sequence of vertices that form the Hamiltonian cycle. I just verify that every adjacent pair is an edge and it has all the vertices and it is a cycle. So, all that is easily verifiable in polynomial time. So, this is an NP. Okay. So, now the $1 million open problem, now I think it is $10 million or something, is what about the following? We know that any problem in polynomial time has a non-deterministic polynomial dimension trivially. But if I tell you a problem is in NP, is it solvable in polynomial time? That means problems that are, so in some sense this is about verification. Problems for which there is a easy proof for S answer, can you also find the proof in polynomial time, right? This is about finding the solution, this is about verifying the solution. So, this question is a famous open problem. But you might ask, didn't you just tell me that Hamiltonian cycle does not have a polynomial time algorithm and it is an NP? So, is it not a candidate problem in NP but not in P? We are not sure, because this does not have a polynomial time algorithm to our knowledge, but there is no proof which tells you that it cannot have a polynomial time. So, this is the fundamental question, right? Are these problems, do they have polynomial time? Problems in NP, can you put them in P? I mean, there are problems in NP for which we do not have an efficient algorithm. P is contained in NP. So, NP is a big thing, right. In the Venn diagram, P is sitting here. So, NP contains efficiently solvable problems also, but there are, so the question is, are there problems here? Is this portion non-empty or are there problems here is the question. So, in particular, a lower bound proof which tells you Hamiltonian cycle or longest path do not have a polytime algorithm would resolve the question, okay. A non-polynomial lower bound, you do not know that, or yeah, okay. But if I tell you that Hamiltonian cycle has a polytime algorithm, will it resolve that question? Not based on whatever I have told you, because it just says that here is one more NP problem which you can put it in polynomial time, but it turns out Hamiltonian cycle longest path actually belong to not just they belong to a special class which we are going to define called NP complete, which means that a polytime algorithm for any one of them will yield a polytime algorithm for all of them, resolving that question. Okay. So, what is that class? That class of problems which we define as NP complete. Okay. So, I am going to give multiple definitions. So, these are problems, they are in NP and every problem in NP reduces to pi in polytime. Okay, I have to define you what reduces to mean, but it is a class of problems somehow that capture every problem in NP. Okay. What does reduces to mean? So, let us use okay. So, is everything okay so far in Pune? Yeah, again. Okay, what does a problem reduces to another problem mean? And we are talking about in polytime, right? Pi 1, these two are problems, and problems, by problems, you can interpret as languages. So, when you say language, it is a, what is the language, right? What is the language for Hamiltonian cycle problem? Set of graphs for which, so these are set of S instances of the problem, more precisely efficient encodings of the set of S instances of the problem. Okay. So, because then it will be all strings, binary strings. We are talking about binary strings that are accepted by the machine. Okay. I mean, so you don't need that. So, just to say that all this can be formally interpreted, but for when we say problem, you know what the problem is: Hamiltonian cycle problem, shortest path, set cover, all these problems. So, we say pi 1, I think this is right, reduces to pi 2 in poly time mean if for every x in sigma star, right, this is our universal language, there exist, let me make sure put the quantifiers correctly. If there exists a polytime algorithm A that, so let us call that okay A, that converts every instance x of pi 1 to Ax of pi 2 such that x is a S instance if and only if y is an S, Ax is a. Okay, here is a simple interpretation of it. We can solve pi 1 in polytime using a polytime algorithm for pi 2. Really, that is what it is. Pi 1 reduces to pi 2 means that if you have an algorithm for pi 2, I can use that as a subroutine to solve pi 1. Okay. Well, that is what this converts, this explains. Why? Because what you do is you want to solve pi 1, okay. Give me an instance x of pi 1, I have to tell you whether it is a yes or no, because that is what the pi 1 problem is. So, there is a polytime algorithm which will take your x and convert it into a of x of this instance in a way that x is an S if and only if Ax is an S. So, I will take x, convert this polytime algorithm, use it, convert it into a of x, apply the algorithm for pi 2, get whether pi 2 is S or no, because you told me there is an algorithm for pi 2. Accordingly, I will answer whether x is a S or no. Okay. This is, it looks very cryptic. We have seen it in our course several times, right. For example, bipartite matching, polynomial time reduces to max flow, right. Which simply says that if you have an algorithm for max flow, I will use that to solve maximum bipartite matching, because I can take the instance your graph problem, convert it into a flow problem by adding an S and a T and some capacities, solve the max flow problem. Based on the answer I get an answer for my max bipartite. This is exactly what reducing means, right? That pi 1 reduces to pi 2 means I can use an algorithm for this to solve this. Okay. Now, this P means this reduction is polytime. So, this reduction is very powerful. Depending on the class you want to define, you can define it in multiple different ways. For our purpose, polytime, okay, because eventually I want pi 1 to be solved in polytime. Okay. You may talk about logarithmic space or 2 to the little o of n or whatever, and then the P, the reduction parameters and constraints will change accordingly. Okay, but for our purpose, it simply says, right, we have seen this, I know selection, finding the median is less than reduces to sorting. Right? If you have done sorting, I can solve median because it's a middle element. Yeah, so that's what reduction means. Yeah, question? Okay, so now let's come back to the definition of NP completeness and notice that it says something very strong. What this says is that these are problems in NP for which every problem in NP reduces to it. Okay, so that means, you know, yeah, that's what it says. In some sense, this guy captures the hardness of every problem in NP. That if you can solve this, you can solve every problem in NP in polynomial time. That's what it is, because pi 1 reduces to pi 2 means that pi 2 is in P implies pi 1 is in P. So, if pi is a problem to which every NP problem reduces, that means we can solve pi in, so, right, hence pi is in P implies and pi is NP complete imply what? NP is contained in P and hence NP is equal to P. NP is contained in P because this tells you that if you can solve this in polynomial time, you can solve this in polynomial time. Pi is such a problem where every problem in NP polytime reduces to this. So, if pi is in P, then every problem in NP is in P, and so NP is contained in P, and we would have settled our conjecture about whether NP and P are the same or not. Okay. Coming up with such a definition is fine because it just somehow throw in whatever you want to achieve into the definition, but then do we know whether this set is non-empty, right? Otherwise, what's the point, right? And yes, so there was this breakthrough result in 1971 by Stephen Cook and Levin independently, who showed the following problem: SAT is NP complete. So, what is a SAT problem? Your input variables, it has some n variables and clauses. So, a clause Ci is an R of something, right? Xi1 or Xi2, maybe some of them are negations. It is a clause like this, and the question is, does there exist a 0-1 assignment for x1 xn that makes all clauses satisfiable. And you make a clause satisfiable. So, you satisfy a clause Ci like this if this variable is true or 1, or this is 0, or this is 0, or so on and so forth, right. A clause is an OR of some variables and their negations, and that is satisfied by an assignment if the positive variables, one of them should have a 1, or the negative variables, one of them should have a 0. And the question is, given such a formula, this is called a formula. So, f is C1 and C2 and Cm. Is there a 0 1 assignment to the variables such that you can satisfy this formula? So, this was the question. Okay, the real SAT problem they looked at was more general than that. They are not necessarily in this what is called conjunctive normal form, but let us say it is in this form. Okay, so is the problem clear? It is a satisfiability. It is a problem in Boolean logic which has a variables in a collection of clauses. Can you simultaneously satisfy all the clauses by setting the excise 0 and 1? Right. So, you may have 3 clauses like this, and you want to know that there is some set of assignments you can set, so that all these clauses are satisfied. So, I might set x3 to 1, x2 to 1, I might satisfy these two, but that means that, so I can set x1 equal to x2 equal to x3 equal to 1, and the rest I do not care, that would satisfy these 3 clauses. Okay. So, the question is there such an assignment? Okay. Is it an NP? Okay. What would be a proof? Assignment, right. You give a 0 1 assignment like I did, you can verify, right, it satisfies. So, you say okay, set x1 to this, x2 to this, x3 to this, and take that assignment. I will go plug it into the formula, verify that it is. Yeah.
They can't see the both actually.
Who? You have to wait for a second. Can you see this side? Yes? Okay, fine. So, I'll write here. So, suppose I have if this is the set of clauses, I may ask, can you come up with some variable assignment such that this set of clauses is satisfied? One such assignment would be x1 equal to x2 equal to x3 equal to 1, and the remaining you set whatever you want. So, this problem, satisfiability problem, is in NP because the S answer, yes, it is satisfiable. If you are trying to convince me, you just have to give me an assignment. I will plug it into the formula and check whether this assignment is satisfied. So, it is an NP. Now, to really prove this big challenging work that every problem in NP reduces to pi in poly time, what do? Well, you take an arbitrary problem in NP, okay. I am not going to give a proof of that because that is a one full lecture. but just want to give you an idea of how that goes. So, SAT is an NP clearly to prove okay. So, this is that every problem in NP reduces to that is also called hardness. So, you can think of it as a problem is NP complete if it is NP and if it is an NP and it is NP hard. These people often ask me what is NP hard, this problem need not be in NP. Okay. So, NP plus NP hard. So, what do they do? Pick some pi in NP and what is my goal? I want in poly time reduced to SAT, such that S, that instance is a S instance if and only if that is an S instance. So, you take some instance here. Okay, what does pi in NP mean? Now, they use the formal definition of there exists a non-deterministic Turing machine that accepts X in polynomial time. So, construct the Turing machine. Look at the states of the Turing machine, the alphabet. What does the Turing machine do? They simulated the entire Turing machine in some logical formula. Okay, so that you see this and you go, then you are in this state, then you overwrite it by this and go to the right. So, this whole thing is written as a Boolean formula in a way that this thing stops and gives a, it's accepted by the machine if and only if this formula has a satisfying assignment. That satisfying assignment will be essentially the sequence of states traversed by the Turing machine to get to an acceptance state. So, this is how they proved, and this I said is coming up with this combination of variables that capture the Turing machine computation is enormous task. It is just basically some assembly language programming kind of thing, if you know what that means. So, that is like a 2-3 page proof. Okay. By the way, when Cook and Levin wrote this in 1971, there was no notion of NP completeness or anything. The paper of Cook is called Complexity of Theorem Proving Procedures or something like that. And 1972, Richard Karp found that actually this result is a gold mine, and he showed a whole about 20 plus problems NP complete. And then the whole industry started, and people even coined the phrase of NP completeness much later. When they saw all this, there was a big survey, and they came up with this notion of NP completeness, because this notion of completeness has been around in formal languages for a while. So, it fit in that definition. So, what did Karp show? He showed a whole bunch of problems, including Hamiltonian cycle, vertex cover, set cover, longest path, Steiner tree, Clique, independent set. Here is a sample of such problems, and he showed them all NP complete. And we will see some of them in today's and tomorrow's lectures, or next Friday's lecture. How did he show them? Well, first you have to show it as an NP. Okay, that is some witness, some certificate, polynomial time verification. Now, to prove hardness, since Cook has done much harder work, you do not have to go and show that every problem in NP reduces to this problem, right. You can just say that some NP complete problem reduces to this. Then through transitivity, you have every problem in NP reduces to this, because there are just two levels of some NP complete problem, it is NP complete. So, every problem in pi reduces to this. I start from here and reduce to me. Okay. It is all about using an algorithm for my problem, you can solve some NP complete problem. and because that is NP complete, every problem in NP can be solved in polytime. So, that is so you can start. So, now the reduction has become easier. You can start with some known NP complete problem and reduce to your problem. Okay. So, let us okay, and because of this, that if an NP complete problem is polytime algorithm, then every problem in NP is polytime algorithm, and people somehow do not believe that NP and P are the same, because one is clearly about verification, the other is about finding solution, and we believe that finding solution is much harder, right, because you all can read papers, but it does not mean that you can actually come up with the results in the paper. So, somehow intuitively we believe that verification and finding solutions are different. So, P and NP are different is a popular assumption about this conjecture, and hence it is believed that NP complete problems do not have a polytime algorithm. So, one algorithm for one of them would imply P equal to NP. So, trying to show a problem is an NP complete is sort of like giving a lower bound, right. This is the cartoon I showed, which says is I can't solve this problem, but so can't these famous people. That is exactly trying to show that there is no polytime algorithm for this, but because it is equivalent to so many other problems. Okay, so that is it. So, now let us try and get our hands on trying to show problems NP complete, and it is all about reducing to problems. We have seen it in the course, like I said, bipartite matching and max flow, and we have seen it. It is just that we are now trying to do it for a different class of problems. Okay, so let us try and show this problem. SAT with at most 3 variables in a clause. And notice that NP completeness is about trying to prove lower bound, right. It is trying to show the problem is hard. So, the more restricted version you show the problem hard, it is a stronger result, right, because you are saying that even with this extra assumption, the problem is hard. Okay, that is what I am saying here, that if you have a formula where each clause has at most 3 variables, even with this assumption the problem is NP complete, but at most 2 variables in a clause solvable in polytime. So, it is in P. Okay, that's a reasonably simple algorithm for a good exercise. So, we may or may not get to this, but let us try and show that. Okay, so how do I show this first of all, right? How do I show a problem is NP complete? First thing is to show that it is an NP, right. It is an NP is obvious because it's again a restricted version of SAT. SAT has been an NP. So, an easy certificate would be satisfying assignment. I just verify that every clause is satisfied. Now, to show hardness, we will take some NP complete problem and reduce to my SAT with. So, what is now always it is a challenge. It is not obvious what is the NP complete problem you choose from. Okay. Another important thing to remember is the direction, right. You do not reduce your current problem to that problem, you start with a known NP complete problem and reduce to your problem. Okay. And what does reduce mean? That for every instance here I have to give one instance such that this is yes if and only if this is yes. I have to do it in polytime. Okay. So, what problem is the more natural problem here? SAT itself, because it's all about SAT. So, let us take the general SAT and somehow reduce to SAT with 3 variables per class. So, you are given an arbitrary instance of SAT, CNF SAT. When I say SAT, I assume that it is in this special form, right, ANDs of R's or R's of ANDs. So, what is the problem with such an instance? Why does it not belong here? Maybe there is some clause which contains more than 3 variables. So, let us pick some clause. Without loss of generality, let us say it has some L clauses, L variables, where L is greater than or equal to 4. Okay. I want to reduce it to some number of clauses with at most 3 variables each, but I want to maintain the sanity that if this is satisfiable, if and only if that is satisfiable, and then I will do this for every clause and then I will be done. Okay. So, the following reduction works, or somebody wants to suggest something. So, this is what I am going to do. I am going to say x1 or x2 or a new variable y1. Okay. This is something new to this clause I am introducing. And dot. Finally, I will have something or x l minus 1 or x l. So, I break a long clause into clauses of length 3, because this instance can have length at most 3, and this is how I break this y1, y2, y3 are fresh variables for this clause. So, x1 or x2 are y1 and y1 bar are x3 or y2, y2 bar are x4 or y3 and so on, and last one yl minus 3 bar or xl minus 1 or xl. Okay. Now, I do this kind of thing for every long clause. These yi's are new, xi's are, between any two of these clauses there may be common xi's, they are all only have xi's anyway, xi's are xi's, but these yi's are special for that clause. So, maybe I can call them y1c, I do not want to mess them up. What do I have to prove now? Yes, what is if and only if? So, let us call, I have this f original formula and f prime is after obtaining this, the claim is okay. So, let us try and prove this, right. I have this formula original, first of all, have we spent polynomial time? That is important, that is very, very important. Okay. I mean, we take it for granted, trying to prove it is an NP and the reduction is polynomial time. Make sure you just verify this. Is it polynomial time? Yes. How many new variables we created? Well, the length is of L, then approximately L new variables for each clause. So, if there are M clauses, then LM new variables. Okay. So, it is polynomial in the number of variables and clauses in my original instance, and the overall length has not increased by much more than polynomial. So, this whole reduction is polynomial time. So, now I am done. If I show that these two are equivalent instances, so then I can reduce to my 3 SAT, check, use my algorithm for 3 SAT to solve this. Okay. So, how do we show this? So, suppose f is satisfiable, what does that mean? See, this, the important thing is y's are your variables, you set them in whatever way you want, that is a beauty. Okay. So, suppose f is satisfiable, then every clause is satisfiable. So, there is some assignment, which satisfies every clause. Let us take that assignment and look at this clause and say that, oh, I know that in that assignment C is satisfied, right. How is C satisfiable? Some xi is satisfied, right. I have made without loss of generality, it is x1 or x2 or x3 or xl bar. You can have bars on some of them, it could be not consecutive, but it does not matter. So, some let us say x5 is satisfying that clause. Now, can I satisfy this clause now? What do I do?
So we can assume the y1 should be 0 for except for that clause, the y
No, if I put 0, then first guy is gone. So, let us say x5 is satisfying is what you said, okay. So, up to so this will be y3 bar, right, y3 bar and x5. So, now since x5 is satisfying this clause, I can set y3 to true, because I do not need y3 to satisfy this. So, set y3 to true, that will satisfy this. I can set y2 to true. So, all the y's up to y3 I will set them to true. So, those will satisfy everything before, and I have here y4. I do not need y4 also to satisfy, set y4 to 0. So, basically all the y's up to that point I set them to true, all the y's after that point I set them to false. I will be able to satisfy all of these clauses. Okay. So, depending on which xi, I know some xi, maybe more than one xi, pick one xi which satisfies this, then I look at that and say, okay, in that class you are satisfying me. So, I am free to choose the yi's. I will make sure that y4 is 0 and y3 is 1. Since y3 is 1, this is done. So, let me pick y2 to 1. So, all the y's before are 1, all the y's after are 0, that will satisfy everything. Okay. And since yi's are fresh for this clause, setting these y's do not make anything else bad. For a other clause, there will be some other special, some xi is true, you go to that particular yi and do this game, and you can satisfy all these clauses. Okay. So, that is a forward direction. Okay. I am not writing it down. Okay. Maybe I can say if, let us say if xi satisfies C, set y1 equal to y2 up to yi minus 2 to false, yi minus 1, yi whatever yl minus 2 to true. Actually, no, I switched it. This is true, this is false. So, if xi is satisfying, then up to yi minus 2 I am going to set them to true, and from yi minus 1 I am going to set these guys to false. Okay. Converse. Okay. Conversely, if suppose this entire formula, the broken down formula is satisfied, I want to argue that in each clause there must be some xi setting to true. Okay. In fact, the way I will argue is that in this formula there must be some xi which must have been set to true, right. So, okay, so how does you have some clause C which is broken down like this, every clause. What we argued is if there is a satisfying assignment for these, then there is a satisfying assignment for all these clauses by looking at one C. Now, conversely, if there is a satisfying assignment for all of this, I want to claim that in each Ci some xi must be true. And the way I will claim is that in this itself, in this satisfying assignment, there must be some xi set to true, because yi's alone cannot satisfy all the clauses, that you can verify, right, because suppose all the xi's are false, then you can't satisfy this, right. What we argued is if some xi is true, this is satisfiable, and this is the converse. If all the xi's are false, you can't satisfy this, because all the xi's are false, and to satisfy this, this must be true, this must be true, this must be, all the yi's must be true, because otherwise how am I going to get this clause to be true? If y1 is true, this is false, x3 is false, so y2 has to be true. So everybody has to be true, which means that all the last clause has to be false. So the simple claim is that this whole thing is satisfiable if and only if this is satisfied. So f prime is satisfied implies f is satisfied. Somehow we are encoding, this whole thing into y1, x1. I mean, yeah. So we want to say we are breaking this whole thing into some y1 and y1 bar or x3 or something like that. I mean, you should find out yourself. I don't think I will be able to explain any more than this. Yeah. So let's just do one more, which is like a graph problem, and then we will continue tomorrow. So let's look at the Clique problem. Is NP complete? So the Clique problem, which has a graph G. Remember, ideally, what is a clique in a graph? It is a maximum subset of vertices which are mutually adjacent, pairwise adjacent. It is a subset of vertices which are mutually adjacent, right? So this graph, this is a clique on 2 vertices. This is a clique on 3 vertices. This is a clique on 3 vertices. This whole thing is a clique on 4 vertices, right? Yeah. So now ideally one is interested in the maximum clique problem. What is, given a graph, what is the maximum subset of vertices which are mutually adjacent, right? The minimum clique is trivial, right? In just one vertex, okay. So, but as I said, we are going to look at decision problem. So the question here is G and an integer k, is there a clique on k vertices? Okay. So this is the problem. We want to show finding a maximum clique or k clique is NP complete. It is an NP. What's the proof for the S answer? Give a subset of k vertices. I will verify that it is actually a subset of k vertices and they are mutually adjacent. It's an NP, right? Now I want to reduce from SAT to clique. Okay, why SAT? We'll see. I mean, as I said, which problem you reduce from is always the hardest thing. You need to carefully, it's not very easy. So you can think of SAT is about simultaneously satisfying a bunch of clauses, and clique is about somehow simultaneously picking a set of vertices which are mutually adjacent. Okay, it's sort of a reverse engineering. Now I know the reduction, I'm going to try and explain it, but so no, but this should tell you what the parameters. So here I have a formula f. Now here I have to construct a graph and an integer k. Both are my choice. Depends on f, right? It's a function of f. So what do you think k should be? Let's think of. It should be m. Okay. Somehow, if you think of a satisfying assignment, is somehow, there is some variable satisfying C1, there is some variable satisfying C2, some variable satisfying C3, so that is some variable satisfying Cm. So, somehow I want to simultaneously pick them all and form a clique. Okay. So, my clique size I am looking for is M. Let us think of what should be the graph. Okay. Let me start with the following, right. So it is like a M-partite graph. C1 has certain variables. I have a vertex for each one of them. This is C2 has a certain number of variables. I have a vertex for all of them. Cm has a certain set of variables. So, some of these variables are same, right, because they are on the same set of variables. So, this will be x1, this would be x1, this could be x1 also, but does not matter. I am going to make a separate copy for each one of them. And let me draw all edges across to start with. Okay. So, all edges across, that is my G. Okay. It will not be the final G, I will do something to it, but let us as a first try. Now, if f is satisfiable, then there is an assignment to the variables that satisfies each clause. So, I picked the corresponding assignment here, let us say maybe x5 satisfies this, x2 satisfies this, x7 satisfies this, x11 satisfies this. I go and pick that corresponding vertex here and they form an M clique, right. But the M clique anyway exists even if it is not satisfied. So, I have to do some surgery to the graph. Okay. Let's try in a reverse direction. An M clique necessarily must pick one from here, one from here, one from here, one from here, because in my graph I made each of this an independent set. So, if you have a clique of size M, it must necessarily pick exactly one from each of these groups. Okay. Now, what would prevent that clique to correspond to a satisfying assignment? Let us see. I claim, oh, you are picking x3 from here, I will go and set x3 here and set it to true. You are picking x7 here, I will go here and pick x7, set it to true. So, that would give me a corresponding satisfying assignment. Will it always give a corresponding satisfying assignment? Where will be a problem? If I pick x3 here for my M clique and it turns out I picked x3 bar here, and then I say hey, here is an M clique, the corresponding assignment, this will say set x3 to true and this will say set x3 to false, and you have a problem. Okay. So, I want to make sure that there are no such edges, that is all. So, in my graph G, I will make it complete M-partite except xi in one part and xi bar in another. Do not add such edges. Okay. Again, very important, people often get confused that I do not know whether this formula is satisfiable or not before I construct this graph. People, I have seen proofs where it will take f and take a satisfying assignment and I will construct the graph. No, you are given only the formula, you have to construct the graph in such a way that this is satisfiable if and only if this has an M clique. Okay. So, but how do you construct it here? These are the things that should go in your mind, right. How I want satisfying assignments to correspond to cliques, right. So, when will, if you pick a vertex here, vertex here, vertex here, when will it not correspond to a satisfying assignment? If x3 and x3 bar. So, do not add those edges in the graph. So, given a formula f, I construct the following graph, which is an M-partite graph, except it does not have these edges, where there is one part is xi, other part is xi bar. Do not add that edges, that is my G. Now, we can, yeah. Oh, remember that is constructed from this clauses, right. So, C1 may contain x5, x2 bar and x7. Then the corresponding vertex here would be, this corresponds to x5, this corresponds to x2 bar, this corresponds to x7. So, I have constructed the graph exactly mimicking these variables. So, there is a copy of whatever these variables are, the literals are, I have the corresponding thing in this graph. Now, I add an edge between every pair of them, but if an x2 bar is here and x2 is sitting somewhere else, I will not add an edge, I will add the remaining edges. Now, we can prove that f is satisfiable if and only if G has an M clique. Right. So, maybe I should have done an example where if you have suppose this is my f, then I will have a graph which will have these two vertices. So, these are the edges I will not add, I will add every other edge, and that is my graph corresponding to this formula. And then I can claim that f is satisfiable if and only if G has an M clique. The forward direction, if f is satisfiable, there is a satisfying assignment which satisfies each of these clauses, pick the corresponding literals, they form an M clique because there is no mutually conflicting pairs of variables here, because I would not have added an edge here. That would not correspond to satisfying assignment. Conversely, if you have an M clique, that M clique must necessarily pick exactly one from each of these groups, collect those, go to the corresponding variables and set them to true. That would give a satisfying assignment here, because there won't be anything mutually conflicting, because that would not have corresponded to a clique otherwise. Okay, so now you can go ahead and try before next time independent set. Given a graph G and an integer k, I want to know that is there an independent set. This is a set of vertices which are mutually non-adjacent. That is NP complete. You can go ahead and check for vertex cover. We have seen vertex cover, have we? Yeah, it's a set of vertices that cover all edges. Try and show these problems NP complete. We will start from them next time.